Dear friends, welcome to Infos. Welcome to another video from Infos on oil and gas training series. In this video, we are starting a new subject, heat exchanger. This is my 53rd video. So this is the heat exchanger part 1. Heat exchanger is a process vessel using in oil and gas industry, not only in oil and gas industry or any type of process industry like petrochemical plant or other plant for heating and cooling purpose. So we will understand the various applications of this heat exchanger. So welcome to this video. So principle of heat transfer we will discuss in first. So what is the in this video we are going to discuss about mechanism of heat transfer and process overview of how the heat exchanger is working, constructional details, process instrumentation control system using in heat exchangers, safeguard mechanism, etc., etc. So one by one we will review it. So let us see the principle of heat transfer. Heat energy will transfer naturally from hot to cold. The difference in temperature will allow a flow of heat to take place until a uniform temperature reach. In production and process facilities, the transfer of heat energy takes place in equipment called heat exchanger. So this is the simple picture of an heat exchanger. Two medium will be there, hot and cold, entering from one side and exiting from the other side. So the addition of heat take place in heaters and extraction of heat take place in coolers. So mechanism of heat transfer. Various mechanisms are using for heat transfers. In school maybe you have studied that one in conduction, convection and radiation. So these are the symbol pictures are representing on three ways of heat transfer. So conduction is the heat occurs by the excitation of adjacent molecule in a solid particle with the molecules have little or no movement. Conduction is the primary mechanism in solids. See here it is there, and heating is taking place the one side, and temperature molecules movement is transferring the temperature from hot side to colder side. So look at that one. This is the way heat transfer is taking place in conduction. This is also another example. And convection is that mechanism where heat energy is transferred by the physical movement of molecules in place to place. In most fluid exchangers, convection is the most important mechanism for heat transfer. Look at that one. Here is the symbol pictorial representation of convection, and here it is both. It is showing that one. Another one is radiation process whereby a body emits heat waves that may be absorbed, reflected or transmitted through a colder body. In boiler and furnaces are using radiation heat transfer mechanism effectively. So the example is heat waves are coming from the sun is best example for radiation. So in this here it is a conduction, convection and radiation is explaining properly. So heat transfer rate is another important one. Heat transfer rate. So the equation is basic equation for heat transfer rate is Q is equal to UA delta T LMTD. So Q is the heat transfer rate and U is the overall heat transfer coefficient. That means it is a thermal conductivity is influencing on heat transfer coefficient. Thermal conductivity of fluid which is passing through the heat transfer and the thermal conductivity of material which is using for the construction of heat exchanger. And A is the surface area which involves velocity as well, and the last one is the delta T, that is a temperature difference between hot and cold fluid, but it is arranging in such a way that one logarithmic mean temperature difference, it is arranging that one to get an effective heat exchange. So the rate at which the heat transfer between fluid must be considered. The main factors are affecting heat transfer are temperature difference, surface area, transfer coefficient or velocity of flow. Let us see one by one. So the first one is a surface area. Look at that one, a symbol image is here to show the total surface area of a heat exchanger. So surface area affect the flow of heat is the area of the exchanger. The basic principle is expressed as follows. The larger the surface area are available for exchange, the greater the amount of heat exchange. An exchanger with 10 tubes would obviously transfer twice as much as one having 5 tubes. The area of the exchanger, an exchanger is the total external area of the tubes in the unit. So that area is heat exchanger area is affecting the total heat transfer rate. So temperature differentials is very important. Look at that one. So the heating cooling medium is entering from one side and hot medium is on another side. So temperature gain is by cold medium is a T2 minus T1, that is a small T2 minus T1 here, and temperature loss by hot medium is a capital T2 minus T1. So this temperature difference for two temperature difference by hot and cold is will arrange in such a way that one delta T LMTD, logarithmic mean temperature difference. That's why it is arranging and designing that one. It will influence on the total heat transfer rate. And temperature difference also, better temperature difference we can make using the flow pattern. Two type of flow patterns are using that we will discuss in our coming video, slides. So the amount of heat transfer varies directly with the temperature difference of the hot and cold fluid. To achieve better heat transfer, we use different flow patterns like parallel and counterflow. Heat transfer coefficient. Some materials conduct better heat better than others. The thinner the material, the better the heat transfer. The properties of material from which heat exchanger is made are used to calculate the coefficient of heat exchanger, an exchanger. It is a measure of the amount of heat that can transfer in 1 hour across 1 feet square of exchanger area of each degree Fahrenheit temperature difference between hot and cold fluid. In the given table, it is giving thermal conductivity of various fluids. In liquid fluids and gas fluids, it is given, and that will also affect the overall heat transfer coefficient, this thermal conductivity of fluids, and plus the thermal conductivity of metal also. Here in the table it is giving various metal, how the in various temperature how the thermal conductivity varying, that also will affect the overall heat transfer coefficient, that is representing here U, that also will affect the total heat transfer rate. And velocity of flow, as I said to you, area is influencing on velocity. So the flow of each liquid is slow, the temperature difference will be about the same and heat transfer slow. And if you increase the velocity so that the flow will be is in a turbulent region, we have maximum temperature difference and greater heat transfer. So exchangers are designed so that flow will be in turbulent region. So for that one, this is the laminar flow. Laminar flow is a straight line pattern, very low velocity. So that is not efficient, suitable for heat transfer. For heat transfer, it is a turbulent flow region. Actually, turbulent flow is designing Reynolds number, which is using in heat transfer. Reynolds number is dV rho by mu. D is the diameter of the pipe, and V is the velocity, and rho is the density, and mu is the kinematic viscosity. So that is deciding Reynolds number. Reynolds number is deciding the flow is in which pattern, either in laminar flow region and turbulent flow region. So that will affect the total heat transfer Q. So flow patterns is usually most commonly using a parallel flow. Look at that one, hot and cold fluid entering from one side and leaving from the other side. That is which is called parallel flow. You can see that one. So both mediums flow through their respective containers in the same direction. And another flow is there, counter current flow. You can see the image. It is hot fluid entering from the other side, and the same side cold fluid is entering from the other side. So counter current flow, both fluids passing in opposite direction. That is a counter current flow. Process heat duty. All heat exchangers are used in the oil and gas industry are required to transfer a certain amount of heat per unit of time. Depending on the application, this is called the heat duty of the exchanger and is usually expressed in BTU per hour. So heat transfer is equal to mass into temperature change and heat capacity. So heat exchanger types overview. Different type of heat exchangers are using for heating and cooling purposes. In this one we will give an overview only, but a detailed study will be in our coming slides. And the most common one is a shell and tube heat exchanger. Shell and tube is there. Two fluids, one fluid will pass through the tube side and other fluid will pass through the shell side, and arranging and exchanging the heat in the efficient mechanism will be there. So application heating and cooling purpose is there. Many applications are there. Another type is a forced draft air cooler, is commonly known as a fin fan cooler. So it is using ambient air is a cooling fluid, pushes ambient air up through the exchanger tubes, and fins are using here for or tubes using for hot fluid, mainly on cooling purpose, using as air as the cooling media. So another type is a radiator type, that is using in our car, radiator type heat exchanger. It is in this one, it is seawater is using for cooling purpose for rotating equipment. Another type is a reboiler. It is heating in high temperature, and most of the case one fluid is changing its phase to vapor. So that is why it is calling reboiler. Used to heat product used in columns. In distillation column it is using. Uses heat transfer fluid as the hot medium. Normally thermosiphon types are using. That principle is using that one. We will study details in our coming slides. Another one is a condenser. In condenser is just opposite of reboiler. That is hot fluid is condensing from one high temperature, it's vapor phase to liquid phase, and the cold fluid is from the low temperature to high temperature, it is increasing. So heat is receiving from condensing fluid to the cold fluid. The function of the condenser is to change a process fluid from the vapor to the liquid phase. The cooling fluid may be water, air, or another special auxiliary fluid, even other process fluid which need preheating. So now it is after this one, for efficient operation of the heat exchanger, we use a number of passes through the tube side and shell side to better efficiency of the heat exchanger. Let us see what is the passes. Heat exchanger passes, one fluid flows through the tube side and other fluid flows through the shell side. Various flow patterns patterns and passes increases the better heat transfer. Selection of fluids through the shell side or tube side is based on various factors. Which fluid is going to the tube side and which fluid is going to the shell side will be selection of fluid in shell and tube, shell side and tube side, that will select various factors that we will discuss in our advanced classes. So let us see that one tube side fluid, how it is taking place. Tube side flow, one pass circulation, the tube medium passes once only from tube C, enter from here, and the entire area of the tube is passing and it is exiting from the other side. Shell also it is one side. So it is a two-side circulation. See, the tube is entering, tube side it is entering from one side and it is going through here and it is exiting from the same side where the entry. So it is a two-time passing through the tube side. So tube medium travels the length of the tubes twice. This gives the twice the opportunity to be cooled against the shell medium. And the multipass is there. Normally 1, 2, 3, 4 tube passes are there. See, 1, 2, then 3, then 4. So 4 passes is there and more circulation will be there. More better and better heat transfer will be there. Let us look at the shell side flow. Shell side it is a single pass is there, that didn't show here. Two passes is here, how it is there, and it is passing through there, and a longitudinal baffles are arranging in between to change the direction of the flow in shell side. So longitudinal baffle forces the shell medium to travel twice over the length of the tubes. So two passes split circulation is also there in the shell side. See, entering from the center and splitting to the both side, the same longitudinal baffle will separate the direction of the flow and exiting from the other side. Additional turbulence is gained when the flow strikes the baffle and split the left and right. and multipass is there. Multipass is how it is arranging. Vertical baffles are arranging in a vertical in a such a way that 1, 2, 3, 4, 5. So more and more turbulence is creating and better heat transfer taking place in the heat exchanger between tube and shell side. This enables the shell flow to change direction 5 times, creating turbulence and giving extra gain in the heat transfer. Vertical baffles are using to create multipasses under turbulence in this case. So multipass is there. See, look, shell and side, boson side, multipass. 3 tube passes are there and 9 shell passes are there. See, 1, 2, 3 in tube side and 1 up to 1 to 9 is shell side passes. So both medium passes many times over each other. Remember that one, shell and tube fluids are not mixing in this case in heat exchanger at all. Mixing is not possible, mixing is not advisable, mixing is will damage the entire heat exchanger process. Thanks for watching this video. We have understand about the basic heat exchanger principle, mechanism, overview of heat transfer, factors influence of various heat transfer process, the heat transfer equation, and overview of various type of heat exchangers and etc., and various passes on shell side and tube side. So let us understand, let us review more and more details in our coming videos. Thanks for watching this video. Have a good day.